everyone, and welcome to your lesson on interpreting graphs of functions. Before we get into the lesson today, remember we've got our review questions that we started doing in yesterday's lesson, just to help make sure that you don't forget any of this awesome algebra stuff you're learning. So our first review question is, what is the inequality that is graphed below? Go ahead and try that. So if we want to write the inequality from this graph, there's going to be a couple things we need to figure out. We're going to want to use slope-intercept form to help us write the inequality. Now I wrote an equal sign here, but I know looking at the graph, how it's shaded tells me that there's going to be an inequality. It's going to be a less than or greater than sign, not an equal sign there. But the form is the same. So looking at this, one of the first things I like to do is I like to find that y-intercept. The y-intercept here is this point, which is at -1. So that tells me there's a -1 there. I also need to find my slope, which is going to be my rise over run. Here on the graph, there's another point here. That's going to help me find my rise over run, because now I can count the rise is 2 and the run is 1. So rise of 2, run of 1, well, that's just the same thing as 2. So I can say 2x right there. Y is going to be on the other side, but I still need that inequality sign. Remember, when we're graphing inequalities, there's two things we pay attention to. We pay attention to what type of line it is, and we pay attention to where the shading is. Doesn't matter which one you start with. I'm going to start with the shading. I noticed that it's shaded below the line, or it's shaded down. That tells me it's going to be a less than sign. It's either going to be less than or less than or equal to. The way I decide which one is by looking at the line here. The line is a dotted line. That's going to tell me it is less than. If it was less than or equal to, this would have been a solid line right there. So our final answer is y is less than 2x minus 1. Our second review question we've got is another inequality. This one says solve the inequality -5x is less than 3x plus 8. Go ahead, try that. All right, for this one, I would personally want to start off by bringing x to one side. So I would come in and say, I'm going to subtract my 3x. That way x is only here on the left side. When I do that, I get -8x is less than 8. My last step, if I want x by itself, I need to divide by -8. Now, part of the reason I'm giving you this particular problem is because I want to check to see, do you remember what we're going to do? I just divided by a -8. We learned if you're dividing an inequality by a negative number, that inequality sign has to change. So I'm changing it from less than to greater than. And then 8 divided by -8 gives me -1. So we get our answer, x is a number greater than -1. Hopefully your brain is all warmed up now and ready to look at some graphs of functions. Our objective for today is interpret graphs. It's just a fancy way of saying read graphs, understand what graphs are saying. And in particular, we're going to be looking at graphs of real-world situations. These are all graphs of functions. But unlike some of the functions we looked at yesterday that were just x and y and didn't have any meaning, these are going to be actual real-world situations we're looking at. So to begin, the first thing I want to do is draw a couple pictures. I like starting with the drawing of the pictures because it's a good way to introduce some of these, and it'll give you a good idea when we go to read the graphs what they're saying. So to start off, one of the most common graphs you see is going to be speed over time graphs. There's a couple words you hear often with these, and those words are, I'm moving at a constant speed, I'm decreasing my speed, I'm increasing my speed, or I've stopped. So we'll go through and draw a picture for each of them. For this first one, if you are driving a constant speed, if I'm in my car moving at a constant speed, what does that mean? Well, constant means your speed isn't changing. The speed isn't going up, it's not going down, it's staying the same. On our graph, what that would look like is as time goes by, the speed is staying the same. So maybe you started at like 30 miles per hour, you're staying 30 miles per hour the entire time. Your speed isn't going up, it's not going down, it's staying the same. The next one is decreasing speed. What do you think that's gonna be? Well, if you're decreasing your speed is going down. So on our graph, it's gonna show as time goes by, your speed is going down. As time goes by, that speed keeps going down. It's lowering. You can probably guess what this graph is going to look like. What would increasing speed look like? Well, kind of the opposite is this one. Increasing means your speed's going up. So as time goes by, we want to show that our speed is going up. As time goes by, our speed is going up. You want to make sure when you're looking at it, the line for decreasing, the line is going down from left to right. And for increasing speed, the line is going up from left to right. Now we've got our last one, stopped. If you are in your car and you're stopped, what is your speed? Well, your speed is 0. So stopped is like a specific type of constant speed, right? If you're stopped, your speed is constant because you're constantly at 0. But the graph's going to look different than this one. This one here, because my line was up here, that's showing that I did have a speed. There's no number, so I'm not sure what it was, but that there is some sort of speed. But we said a moment ago, when you're stopped, your speed is 0. That would be a line down here. 0 is always right there. So that would be a line right here, showing that my speed is 0 as time goes by. So these are the first types of graphs we're going to look at. The second type, I think, can be a little trickier, and that is going to be distance over time. So we're going to look at those same 4 words, but the graphs are going to look different because we're talking about different things. So I'm going to say I'm moving forward at a constant speed. What does that mean about my distance? If I get in my car and I'm moving forward at a constant speed, what's happening to the distance? Well, your speed might not be changing, but your distance is. If I started on this side of the board and I walked forward at a constant speed, my distance changed, right? My distance from my starting point is going up. On our graph, what that's going to look like is that same idea. If I started here 0 feet away from this side of the board, as time went by, when I was moving forward at a constant speed, my distance was constantly increasing. It's going to be a straight line like that. Now, what about decreasing speed? If you're decreasing speed, another way to think of that is you're starting fast and then you're getting slower. So let me do that same thing. Let me start at this side of the board, and I'm going to start moving forward really fast and then decrease my speed. I'm going to slow down. So I'm going to start moving really fast, and then I'm going to slow down. It's me moving little tiny baby steps. Well, what happened? What happened to my distance? Well, at the beginning, when I was moving fast, I moved forward a lot. And at the end, I was still moving forward, but I was just taking like these little baby steps because I'm moving very slowly. So I didn't move forward as much, but I still moved forward. My distance still increased, which can be a little tricky to understand. I see the word decreasing, but even when you're decreasing your speed, you're still moving forward, right? When you see a red light at a traffic stop, you decrease your speed, but you're still moving towards that traffic stop. You're still moving forward. The graph's going to show that. Even though I was decreasing my speed, I still moved forward. My distance still increased, but it increased differently than before. At the beginning, when I was moving fast, I took that really big leap. I moved really far in a short period of time. The end, when I was taking those little baby steps, I was still moving forward, but not a lot. So on our graph, it's going to show I'm moving forward a lot at the beginning, but as I slow, the line changes direction. As I slow down, it gets flatter. This part right here is where I was moving really fast. And then the end, this was when I was taking those little baby steps. I was moving forward, so I was moving forward just like a little bit. I wasn't going, the distance wasn't increasing a lot, but time was still going by. Increasing speed is like the opposite. It's like putting these two things together, but in the opposite order. If you're increasing your speed, you're starting slow at first and then speeding up. So that would be something like I'm starting slow at first and then speeding up. If you're increasing speed, you're still moving forward. The distance is still increasing, But in the beginning, when you're moving really slow, your distance doesn't increase a lot. But in the later time, when you're moving really fast, your distance increases a lot in a short period of time. So they're both curved, but they're curving different ways depending on the speed. Now the last one, my favorite one to imitate, stopped. Let's say I'm standing here in the middle of the board and I stop. What's happening to my distance right now? If I'm saying this point here is 0, how far away am I from this side of the board? Maybe 1 foot, and I'm stopped. Is that distance from this side of the board changing? No, I'm still 1 foot away. I'm still 1 foot away. I'm still 1 foot away. So when we go to graph stopped, the distance when you're stopped isn't changing. I'm not getting further away. I'm not getting closer. It's staying the same. It would be a horizontal line like this. Maybe if this was 1 foot away from that side of the board, I was 1 foot away the entire time. So it would be that horizontal line. Like I said, I think these are a little trickier because it's still describing speed, but you have to think about what the implications are for distance. You can use these pictures here to help you with the next part. So if you have not drawn some of these pictures down, I would encourage you to do so, because the second part of this lesson is going to be on actually reading these graphs. Me giving you a graph like this and asking you, what was that person doing? The first example, before we get into distance and time, instead we've got a graph of chocolate milk. The story part says, Savannah noticed that the price of chocolate milk at her school has increased at a constant rate since she was in first grade. Which of the following graphs accurately represents this situation? Well, there's a word I would underline here. I would underline increased at a constant rate. I'm underlining that because that's giving me an idea of what the graph should be showing. I'm looking for that price to increase at a constant rate. Looking down here at the graphs, there's a couple that I personally would immediately eliminate. After reading through this, there's a couple graphs that I see and I'm like, I know that is not a graph of something increasing at a constant rate. What are ones you would want to eliminate? Well, usually in class, students say A. I would want to eliminate A. If I asked you why, well, look, it increased and then it stayed the same price. In first grade, it was 15 cents. Second grade, it was 15 cents. Then it increased again, and then it stayed the same. Then it increased again. That's not constant. That's anything but constant. That's very bumpy. The other one students like to say a lot is C. C is showing it's increasing a lot in those earlier grades, but then later on, maybe it's still increasing, but not a lot. It's not increasing by a constant amount. That leaves us with B and D. In order to figure out which one is correct, they look pretty similar, so I'm going to want to know what is different between the two of them. What's the difference between graph B and D? Well, if I look at the grade levels, graph B says 1, 2, 3, 4, 5, and graph D says 5, 4, 3, 2, 1. Which one makes sense? Graph B does. If I'm looking at graph D, what D is actually showing, if you think about the order in which you go through grades, it's showing it is most expensive early on, and then it's constantly decreasing as time goes by. The graph is the opposite order of what we would want. So we get graph B for this one. I've got two other examples, and I'm going to have you guys try some. The next one is, which path below would describe a race car that started slowly at first and gradually increased its speed? Go ahead and try this one. Well, just like before, I would underline some keywords. Here we're looking for something that is slow at first and increasing its speed. We drew a graph of that. Now, for me to decide which one is correct, I also need to pay attention to what these graphs are saying. We saw at the beginning of this lesson, sometimes you're looking at speed over time graphs, and other times you're looking at distance over time graphs. These right here are distance graphs. That is going to be important in me deciding which graph is correct. If it's distance over time, if you are starting slowly at first and increasing your speed, what's that mean about your distance? Well, it means if you're starting slowly at first, you're still moving forward, but not a lot. But then as you speed up, you're moving a lot further. So I'm going to need the direction of my line to change. If I'm looking at this one here, this is a constant speed. I'm moving forward the same amount each minute or second, whatever you're measuring time with. This would be constant, a very slow constant speed, because look, we're not moving very far. So it's not going to be that one. This one here, well, this one shows the distance didn't change at all. So if my distance isn't changing, that's telling me I'm not moving. And then here, similar to this one, that would be constant, but like a really fast constant speed. But that's not showing slow at first and then increasing speed. So it's not this one. These last two are showing the speeds changing. I know that because the line's curved. This part right here is showing the distance increased a little bit, but not too much. So if I think about if my distance is increasing a little bit, but not a lot, that must mean we were going slow. And then the second part here is when we are moving faster, because the distance changed a lot. This one here is the opposite. This would be fast, then slow. Which is the one we want? Well, we want slow at first and then increasing speed. So that would be graph X. W would be a graph of someone decreasing their speed. There is one last one. The last question I've got for my examples is, on the position time graph below, which car is moving at a slower speed? There's a key for us. It says these longer dashed lines are going to be car A, and then the little dotted line is going to be car B. What do you think? Which one is moving at a slower speed? Well, if I'm comparing the two, I noticed that car A went a lot farther than car B. Car B got this high, which means their position or their distance was about that far, whereas car A got this high, which is showing me their position, they got a lot further. So car A went a lot further than car B. We also have to look at the time here. Car A didn't spend as long of time as moving as car B. So let's summarize. Car A went really far in a shorter amount of time. Car B didn't go as far and spent longer not going as far. What's that mean about their speeds? Well, it means A must have been moving faster than B. B must have been moving slower. If we look at the question is who's moving at a slower speed? That would be car B. I like C. Option C says both cars have the same speed. What would this graph have looked like if they both had the same speed? Well, think about it. If you're in a car and you've got a friend in a car and you're right next to each other and you start moving forward at the same speed, well, you're going to be together the entire time. If I graphed two cars with the same speed, that would have been, here's car A, car B. If they're moving the same speed, they would have been in the same spot. It would have been two lines right on top of each other. The fact that the lines are in different places are showing they're moving at different speeds. Now, I think this graph in particular is a good graph to connect what we're doing today with something you guys already know how to do. I'm paying a lot of attention to the direction of the lines. I was saying this line was a lot higher than this line. I could also say this line is a lot steeper than this line. What other thing did we talk about a lot with directions of line? We talked about slope. Slope is the direction of a line. We can connect all of this stuff with speed back to what we learned about slope. If I'm comparing these two lines, this line is steeper. We learned that steeper lines have bigger slopes. A lower line like this, lower lines have smaller slopes. What this means is slope actually tells you the speed of something. Any line that has a bigger slope has a bigger speed. Any line that has a smaller slope has a smaller speed. So there's a place for us to put that down. If you're at home taking notes, I would write this part down too. It just says the slope of a line shows the speed. What does that mean? Well, it means the steeper the slope. If steeper is a weird word for you, you can think about it as like higher the slope or the bigger the slope. I guess I should say the higher the line or the bigger the slope. That means the faster the movement. So if I'm looking at a distance time graph and one of my lines looks like this and one of my lines looks like this, the higher that line, the bigger the slope, means the faster they're moving. I don't need any other information. I know whoever's in this graph is moving faster than whoever's in this graph just because the line is higher. I'm going to go ahead and erase this, and it is time for you to try two practice problems. The first one says, which graph best represents the motion of an object whose speed is increasing? Make sure you're paying attention to these are distance over time graphs. So the one that would be increasing is graph 3, showing slow at first and then the speed increases. The other question is, which position time graph describes a train that leaves the station at a slow speed, stops, then returns to the station at a faster speed? Let me label them for you. This is A, B, C, and D. All right, we're looking for a graph that has 3 things on it. The first thing I need is showing that it's leaving at a slow speed, then it's stopping, and then it returns at a faster speed. Just by knowing there should be 3 parts to it, this one right here kind of sticks out to me as wrong. If I look at this, this is showing the distance is starting up here. It means it's not starting at the station. It's starting some distance away from the station. The distance doesn't change for a real long time, which means the train isn't moving. And then the distance goes up. So it means it finally starts moving and it's moving away from the station. It's not returning. So this one, I am confident, is not right. Now these other 3 here are similar. We are looking for one that starts leaving at a slow speed. So if I'm looking at them, this definitely looks like a slow speed. I know that because it's lower. This one also slow speed. This looks kind of high to me, but I'm not going to eliminate it yet. Then the next part is we want it to stop. We're looking at distance graphs. What is happening to the distance when you're stopping? Well, if you stop, that distance isn't changing. If you're stopping, you're not moving further away, you're not returning. The distance is staying the same. That should be a horizontal line. If I look at these 2 here, they don't have horizontal lines. That means these 2 trains never stopped. This is the only one that's showing me a stop. This is showing me it's leaving at a slow speed. It's stopped for a while because the distance isn't changing. And then if it's returning to the station, when you return, means your distance is going down. You're going back to that starting point. This right here is showing that the line is going down, meaning it's returning, and it's returning at a faster speed. These other 2 here, this one's showing it's leaving really fast, and then immediately, in that split second, it changes directions. It never stops. It just immediately changes directions, starts returning at a slow speed, and then look, it never gets back to the station. It just stops at the very end, some distance away. This one here is leaving at a really slow speed. In that moment there, it changes speeds. It's still leaving, but it's leaving at a faster speed. And then right here in this moment, it changes directions, starts returning at a fast speed. So these 2 here are similar to what we want, but not quite in the right order, because here the stop is at the end. And this one here is never stopping. These were all examples on reading graphs, matching a situation to a graph. The last part of this is going to be on me just giving you a single graph and then asking you some questions about it. So the last part we've got is this graph here. Before I start reading through the questions, let's just look at the graph. What do we notice? Well, we notice it doesn't have a title. It just says graph 1. but I'm going to read my x and my y-axis. I see that y-axis says distance in meters, that x-axis says time in seconds. We've got 3 beautiful pictures of 3 people. It looks like they're running. We've got Albert, Bob, and Charlie here. And we've got this graph is showing then 3 people running and their distance, how far they've run over time. Let me come over to my questions now. The first question says, describe Charlie's speed from 8 to 13 seconds. Well, on my graph, I want to find Charlie. Charlie's here in green, and I want to find him from 8 to 13 seconds to figure out what he's doing. So this green line here, 8 seconds is right here. So I'm looking, there's my start time, and they're asking me about 8 to 13. So 8, 13 isn't down here, but 13 would be in between that 12 and 14. So 13 is about right here. So they're asking what is going on right here. Well, it's a distance graph. So if I have a horizontal line like that on a distance graph, it means the distance wasn't changing. It wasn't going up or down. What's that mean Charlie's doing? It means Charlie stopped. If his distance isn't changing, he's not moving. So to answer the question, describe Charlie's speed, you could say Charlie isn't moving. You could say Charlie stopped. You could say Charlie's speed was 0 meters per second. All of those would be good. I'm just going to say Charlie stopped. In class, some people have a lot of fun with these. I've gotten like, oh, Charlie got so tired, so he needed a break and to drink some water before he kept running. You can have fun with it if you want, but really I'm just looking for Charlie stopped. Our second question says, describe Bob's speed from 8 to 13 seconds. So we're looking at that same period of time, but now we're looking at Bob instead. So I'm going to do the same thing. Let me find Bob on the graph. Bob is this blue line, so I'm going to start here at 8 seconds and go until 13 seconds. So this stretch right here, we're going to forget about Charlie. So what's Bob doing there? Well, if you look at this line, it's curving ever so slightly. We learned a curved line like that means something. As the line is curving, when it gets up here and it's a lot steeper, it means he's moving a lot further in a shorter period of time. That means his speed is increasing here. Down here, this was when he was moving a little slower because the line is flatter. Up here where the line is steeper, it means he was moving faster. So if I wanted to describe his speed, I could say Bob is starting slowly and then getting faster. You could also say he's increasing his speed. That's what I'm going to say. I'm going to say Bob increased his speed. Again, you can get creative. You can say Bob was worried he's going to lose, so he starts speeding on up. All possible options. But I'm looking for something that says he's increasing his speed. Something along those lines. The next question says, describe who finishes first, second, and third in the race. Before we answer this question, think about what it means to win a race. Specifically, what it means about your distance and time. If you win a race, what does that mean about your distance and time? Well, it means you got to the end distance, which here on the graph is 100 meters. It means you got to that end distance in the shortest amount of time. So if I'm keeping that in mind, Albert got to that end distance of 100 in 12 seconds. Bob got to the end of our distance in 14 seconds. And Charlie took, that would be 17 seconds. So who won the race? Who came in first? Albert did. Albert did because he had the smallest amount of time. So if I wanted to answer this, I'm going to put my answer down here. I could say first was Albert. Second then was Bob because he had the second shortest time. So second was Bob. And third was good old Charlie. When I ask students sometimes, well, why did Charlie lose? I'm not asking for your opinion, really. And what I mean by that is some people will say, well, Charlie lost because he took a break. And that could be the reason why. But I could draw Speedy Samantha over here, who just starts off way faster than the rest of them, still takes a break, but then still finishes in the shortest amount of time. So it is possible to take a break and still win. So my reason for why Charlie lost isn't going to be because he took a break, although that definitely could be part of it. My reason for why Charlie lost, though, definitively why he lost, is because he took the longest amount of time to get to the end of the race. If I asked you that question, you really want to get at what does it mean to win a race? What does it mean to lose a race? There's one last question. Describe Albert's speed throughout the race. That just means describe what Albert's doing from the beginning of the race to the end of the race. If I find Albert, he's our guy in red here. If I focus on what he's doing the entire time, I notice the entire time his line is curving up like this, which is something we already talked about with Bob. Do you remember what we said? It means he is the entire race increasing his speed. He's just getting faster and faster as he gets closer to the end. So describe his speed. We can say Albert was increasing. Sometimes I'll get answers just like that. Albert was increasing. You got to tell me increasing what? Increasing his weight? Increasing his height? What is he increasing? He's increasing his speed throughout the race. You could also say he started off slow and then sped up. It's the same idea as increasing his speed, but make sure you're mentioning something about speed in your answer and how he's increasing his speed. That's the last example I've got for you guys. I'll clear this board and give you one last one to try yourself. Our last one says, the graph below shows the progress of two bikers in a 5,000 meter dirt bike race. The first question asks, who won the race? How do you know? Well, here it said it's a 5,000 meter race. So who won the race? Well, A is the only person who got to the end. B right here at 14 minutes. B was only around 3,000, 4,000 meters. He didn't get to the end. So A won. The second one says, describe racer A's speed between minutes 5 and 7. Between 5 and 7 is right here, this flat part. His distance isn't changing. So if his distance isn't changing, that means he wasn't moving. It means he stopped. The last question says, describe racer B's speed between minutes 5 and 7. Well, between 5 and 7, racer B is right here. That line is a straight line. It's not curving, which means his speed isn't changing. It's a straight line like this, which is showing he is moving forward at a constant speed. You would want to make sure you're using the words constant speed. This is the last example I've got for you guys. Thanks so much for watching. We have finished our third unit. Remember we said yesterday, it's a very short unit. We started our unit on functions yesterday, and we ended our unit on functions today, which means after today, there's only one unit left. So get excited. We're getting near the end of algebra. Thanks so much for watching, guys. Bye.